Hello, everyone. Please welcome Ivan Rungger for the next talk entitled Dynamical Mean Field Theory Algorithm and Experiment on Quantum Computers. Please take it away, Ivan.
Okay, thanks very much, Gabriel. Yes, hello, good afternoon, everybody, and thanks very much for attending this talk. I will present our results on dynamical mean field theory on quantum computers, both the algorithm and then some experimental results on quantum hardware. Before starting, let me just thank all the co-authors and the people that have discussed with us this project. So all my colleagues at MPL in the top line, then our colleagues at Cambridge Quantum Computing, with which we started this project, then our colleagues at Wrapup and UCL, who then also joined the project, and Norbert Linke's group in University of Maryland, where they run the ion trap experiments. And then for general discussions, the groups of Cedric Weber at King's College London and George Booth. And finally, Dan Brown at UCL mainly within the Prosperity Partnership, UCL, Bristol, and Google. So at MPL, which is my institute, we do generally work on metrology for quantum circuits because we're a measurement institute. And we have a long history of working in the area of quantum computing, and mainly for understanding the material causes of decoherence. So this goes back like maybe 10 years or so, but it's ongoing work, right? And out of this, a lot of new activities have come out, especially on the experimental side, where they're working on new instrumentation for qubit metrology. So for example, here I show a figure of a single photon near-field scanning microwave microscope, where the idea is that you scan a qubit, a superconducting qubit, and if you find a defect that causes decoherence, it will light up, say. So it would then allow you to track these defects, understand them, and actually hopefully then eventually remove them. But in general, they work on all sorts of systematic measurements, fluctuations and noise in qubits. Then we also have the kind of software group, the theory group, which is where I'm in. And we support the experimental colleagues, right? We do models for them, looking at sources of decoherence, calibration and errors, but also, and that's what I will talk about today, we do develop new algorithms also for benchmarking, testing, and applications. So what systems are we interested in? Now, my background is in condensed matter physics, and these are really the systems I've considered in the last couple of years. It's generally simulations of solids and interfaces, where here I show 3 interfaces that we have published recently with experimental colleagues. But the common property is that there's a molecule kind of in contact with, say, typically a metal substrate. So here we have a magnetic metal substrate, here graphene, and here there's gold. And the tools that we use for these are typically density functional theory, because that's the tool that allows us to have a good compromise between accuracy, but also, you are able to do realistically large systems. And especially it can treat quite well both the molecule and the matter, right, within limitations. So the two systems on the left here, I can get away with just DFT, and I just need to do maybe some minor mean field corrections, and I can get very good agreement with the experiment. But for example, for the one on the right here, where we have condo physics, if I just do a DFT calculation, I don't match at all the experimental data, right? And I need to go beyond that. So without going into details of what condo physics entails, the signature is at low bias and very low temperatures. If you measure the conductance as a function of bias, you see a very sharp peak at 0. And this is a signature of the state in which the system is in. Now, when I do a DFT calculation for this, I get this dashed line here, essentially nothing, right? Just a very broad feature. So to overcome this, one needs to go beyond DFT and consider many-body interaction between the electrons. And what we use here specifically is the Anderson impurity model. And if you do that, then actually our simulation in the blue curve here matches very nicely the experimental data. And actually for periodic systems, this you would basically repeat your Anderson impurity model periodically, so to make a crystal essentially. And that's what dynamical mean field theory in essence does. So we can do this, right, on conventional computers. The problem is that it scales very badly with system size, right? And that's really where quantum computers hopefully will be able to help us. And that's what we're going to look at today. So in general, all the figures on the previous slide are part of what we call embedding theories, right? Where we have a single, say, impurity, where we consider the on-site electron-electron interactions with some parameter u. but they're coupled with some hopping element V with a bath. So the electrons can move in and out. And in terms of names, again, if you have a single one, it's an Anderson impurity. If you make it periodic, so like a Hubbard model, then within dynamical mean field theory, that's the appropriate theory for periodic systems. And we're going to look at both of them today. So there's many ways to solve the Anderson impurity problems, and each is used in a very specific, say, approximation when it's appropriate. To run it on quantum computers, the most straightforward way to do it is what we call exact diagonalization, where in essence you simply replace the bath, which is infinitely big in principle, with a finite number of effective sites, in this case 8. And then for each site you have some parameter like epsilon I is the onset energy and the hopping V that couples this bath site to the impurity site. And then essentially now we have transformed these infinitely big systems to a big molecule, and then we can just solve it using methods used for molecules essentially. So in principle, we can do this, right? We can calculate the Hamiltonian for this big molecule, we can diagonalize it, and we're done. But the problem is that the Hamiltonian size dimension scales exponentially with the number of sites. So on a classical computer, you can only do something like maybe 10 to 20 sites, right? Really depending on how many approximations and what output you want from your computation. And this is some sort of hard wall there, right? We cannot really go beyond that. That's really the problem because it's exponentially scaling. So let's do it on a quantum computer. So I just give you the equation. Now, the quantity that we're interested in here is the Green's function, G, which in essence, without going to the detail, and this is just one possible representation here, the lemma representation, is a sum of poles where each pole has a coefficient, if you want, lambda, right, which gives the height of that peak, and some eigenfrequency omega I, say, right? So once you have all these lambdas and your omegas, you can then just use this equation to get the Green's function. So the algorithm is illustrated at the bottom. You have an input set of parameter, epsilon and V, which characterize the molecule, is the Hamiltonian, basically. Then it's the tricky bit. You have to solve it using this Anderson impurity solver. But assuming you can do that, you get all these eigenfrequencies and coefficients lambda. And with that, with this equation, you get the Green's function, and then straightforward also the self-energy, which is a related quantity. Now, maybe just as a side note, in terms of scalability, in principle here, when you make the system bigger, also the number m here will scale exponentially with system size. You will have exponentially many excited states. But actually, in practice, we always cut it, right? We just care usually about, say, an energy around the Fermi level, typically. So we just care about the first few excitations, which makes it scalar, right? If you would calculate all of them, obviously that's not possible. So that was the Anderson impurity model. Now, dynamical mean field theory, the only additional step now is that you have your impurity repeated periodically, essentially, as illustrated here with these blue dots. And then what you do is you select one of them and you say, that's my actual Anderson impurity. And all the other impurities, you call them Silabath, right? Now the bath consists of all the other impurities. You can still solve it, right, as a system bath plus impurity. Now the only difference is that once you have solved it, this will affect the bath itself, right? So you need to put once you have the output, the input parameters will depend on the output. So you have to cycle this in a loop until you reach essentially self-consistency in the bath parameters. But the computationally difficult bit is still the Anderson impurity solver, right? The loop outside is difficult maybe in itself to converge, but it's a classical optimization, fitting optimization loop. Okay, so how do we do it on a quantum computer? Well, essentially, this is the algorithm from the previous slide, right? We now replace the Anderson impurity solver, the classical one, with a quantum, right? This is just supposed to illustrate a quantum kind of circuit here. And I would say the approaches that have been proposed so far are, I would say, mainly three. So the first one is to do a real-time evolution of this Green's, of the state and the Green's function. And then you can take the Fourier transform to obtain these quantities, omegas and lambdas, basically, or you do some fitting to obtain these quantities. Another way is, again, time evolution, but you do a variational quantum simulation. So it's somewhat, say, a more efficient way to do the time evolution, essentially, but it's still time evolution. And alternative, which is what we used, is that you say, well, because we just need total energies, ultimately, we can just use VQE, as shown also today in some talks before, to calculate the ground state and excited state, and then we input that in our model for the Green's function. And that's what I will show today. Yeah, so this is basically just to summarize what I've said so far, right? We start from the real system of interest, right, which is quite challenging. But okay, let's discretize it. We have an impurity with some bath orbitals. And what we did, because we wanted to run on quantum hardware, we said, okay, let's take the smallest possible system, which was also considered in the literature before, right, theoretically, which is just two sites, one impurity site and one bath site. So it's two-site DMFT. You cannot be smaller than that. And we have one parameter U on the impurity and just one V that couples the two things. And that's what I will show now of how we do it, the algorithm, and then the experiments on the hardware. Okay, so what do we need to calculate? Let's remind ourselves, we need this Green's function, which is given by this top equation, right? The sum of this lambda I, say, and with some coefficient omega minus omega I, say. Now, for two-side DMFT, we have only two, so the only independent parameters are omega 1 and omega 2, so two eigenfrequencies, and one independent lambda. Now, this is actually at particle hole symmetry, which makes life a bit easier. We did the same in the paper for off-particle hole symmetry, in which case you need a few more omegas and a few more lambdas. So we did both. And what you do then, you do VQE for the ground state. So just to the energy is the minimization over some parameters theta of your ansatz for the wave function of the energy, which is a standard VQE essentially, right? We have a given Hamiltonian. Once we have this, the second step is we need a few excited states, in this case two. In this case, it's a 3-electron ground state, so En 3, 0, so the ground state of 3 electrons. And the difference in energy with the ground state gives you the first eigenfrequency, and the first excited states at 3 electrons gives you the second eigenfrequency. How do we calculate this? Well, we could impose the number of electrons by choosing the ansatz that has that number of electrons built in. But what we did in practice in the paper is we put a penalty term in the Hamiltonian that basically shifts down the energy of 3-electron states, so that we basically get this 3-electron energy as our ground state. And then to calculate the excited states, we use these methods to kind of orthogonalize to the previously obtained states. But as we have seen today, there's also other methods to do that, so this is an evolving field in itself. Now, once we have these, there's just the overlap-like matrix element to calculate lambda, which is given by this equation here. So you need the wave function of the ground state with the Pauli X in the middle, and then the wave function of the 3-electron ground state. Right? And this requires a circuit that is just a post-processing essentially. Okay, this is what we have done, and I will show you now the results for this. Maybe just before continuing, just a note on scalability. So obviously, ideally, we want them to scale this up to bigger systems from the two sides. Well, let's look at the 3 steps. Now, the first step will be as scalable as VQEs in general. So all the effort that people work on, do on developing VQE for bigger systems, we can just use it and then get the ground state energy and the wave function of the ground state. So that's hopefully, a lot of progress is made in that direction. For the excited states, the same thing. We only need a few. That's the important thing. So it's not, we don't need all of them, which makes it scalable. And yeah, then again, we rely on methods to calculate excited states using these quantum computers. The last one, the overlap matrix element. I mean, if the fidelities for this circuit is big enough, again, is good enough, then you can compute it. So the bottom is that this is scalable. All right. Then now, let me show actually what we did for this specific system. So we have two sides, 2 spins per side. That means 4 qubits in total, right? 2 times 2. And we want to get this ground state energy. And we see that we tried the circuits, and obviously we took the shortest one we could find, and that was this one here, where you have a few rotations on the left, a few rotations on the right, and 3 C-naughts in the middle. This minimizes this Hamiltonian here at the bottom, which is valid for particle hole symmetry, and just is valid a few terms here. And importantly, with these ansatz, we can reproduce the exact energy, right, which is quite important for benchmarking. So all the deviations will due to other reasons, but in principle, the theory gives you the exact energy. When we extend this now, for example, to off-particle hole symmetry, the Hamiltonian, we get more terms, and then we have tested as well, and we find that actually we can again get the exact analytical energy, but we need to add one more rotation, for example, here in the middle. So with this circuit, we can cover essentially the whole space for particle hole symmetry and off-particle hole symmetry. Yeah, so in principle, and this was just a matter to run on the quantum hardware, which we did. But then what we found is that the results are very noisy. And so we said, well, let's try to just to test and benchmark, can we use symmetries of the system to reduce the number of qubits and reduce even further the circuit depth? And yes, one can do that because we know that the ground state has 2 electrons and a spin of 0. So if you apply this, this knowledge to your Hamiltonian, you can restrict the total number of states. You can reduce the size of the Hamiltonian to what is written here, to a 2-qubit Hamiltonian. And now, obviously, the circuit is very short for our ansatz, just 3 rotations and only one synod. And then we do the same for the 1-electron system and for the 3-electron system, right? So the difference between left and right is the left can do every electron system. This contains all the physics. On the right-hand side, we constrain the electron system to a subset, and then we reduce the circuit, but we have to use a different Hamiltonian for each of them. Okay, and so we now show results for 4 qubits and 2 qubits on the quantum hardware with these 2 approaches. So let's start. So here I show tables with numbers, essentially, and I show all the 4 relevant quantities. E0 is the ground state energy, E30 is the ground state energy of 3 electrons, E32 is the first excited state energy of 3 electrons, and the lambda is this kind of coefficient overlap-like matrix element. In this column is the exact analytical value, right? This can be computed. And here's what we get on IBM's machine on 4 qubits, where we first optimize all the thetas of your ansatz on a conventional computer, and we just fix them. We don't re-optimize them on the quantum hardware. If you look at the numbers, so it's -5, 1.5 instead of, say, -1.8. So it's close-ish. We are off by about 20%, right? That seems to be what we get on this hardware. Obviously, this will depend on the hardware you run, right? The better the fidelity, the better this agreement will be. But it looks promising. And then for the lambda, the agreement is not very good, right? It's like off by more than a factor 2. And which is actually what prompted us to try the 2-qubit solution. And that's what I show here. Again, optimal theta. And now we go quite close to the exact number. So it's 1.7 of 1.8. And the excited states energy are quite close. And even the lambda is now is within at least the same 0.2, essentially, right? And for this, now we said, let's run the full VQE loop on the quantum hardware, which is shown here. And now actually the numbers are very close to the exact ones. And actually they are within the statistical noise measurements that we do. So we do, I think, 8,000 shots here. So that's essentially giving this noise here. And as one expects, the VQE can only reduce the energy, right, in comparison to the optimal theta. So it means that there's some compensation for small calibration errors in the hardware, so you can go closer to the exact energy. So this looks very good. And we did the same just to compare on the trapped ion machine in Maryland, where, again, I report the same number, not the full VQE loop, but just the optimal theta results. But here, the main difference is that on 4 qubits, already the energy is quite significantly closer to the exact one. And also the lambda actually is already quite close. And if you go to 2 qubits, it gets even closer here. So this was good, and we were quite glad about these results. But this is not the end. As I said, if you want to do the full DMFT loop, but this is the Anderson impurity model, that's a single impurity. But actually, these numbers come from a Bethe lattice, which is a periodic system. So there's a self-consistency condition, which was the next step that we needed to solve. And the self-consistency condition is shown here. The B square, which is if you remember, the coupling between the impurity and the bath site, has to be equal at self-consistency to Z, which is the quasi-particle weight, but is essentially a function of the self-energy sigma at delta is a very small number, so close to 0, essentially. This we can compute. And then the idea is that you start with a random guess for V, and hopefully then you converge to the correct solution. And that's what we do here in this graph at the bottom here. We start at 1, which is just a random initial guess for V. And this is 0.75 is this exact result. And at the beginning, it goes down quite nicely, but then actually it started to oscillate around a lot, and essentially it doesn't converge. So this is not very good. But actually, we did expect this because, as I said, it depends on the value of the self-energy at 0. And we knew already by previous analysis that when we plotted this, maybe it's not so visible on this graph, but the exact number here at 0 is a very continuous blue curve in the background. But actually, if I put a bit of error in my solution, I actually get an unphysical pole or a peak at that energy, right? So clearly, depending on the exact height of this peak, I will jump all over the place, basically, right? So although my numbers were within maybe error, within well, actually this was simulation, so it's just a statistical measurement noise. So I'm very close to the exact solution, but it's enough to still make the solution so wrong that I cannot converge. And so we did analysis of this, and the reason for this kind of peak here is that the self-energy is actually a difference of two quantities, the non-interacting and interacting Green's function. And it just so turns out that if the solution is exact, each of them is a pole by itself at 0, but if the solution is exact, they exactly subtract each other out, so nothing remains, and we have a very nice and smooth function. But if your quantum computer gives even just 1% error in your result, you will have a pole, right? That's really a problem. But luckily, one can come up with some sum rules here, which we derived and adapted to this specific system that essentially give you one more equation. It can be done in a scalable way that in this case basically tells you what lambda has to be as a function of omega-1, omega-2. So really you don't have three independent parameters, but once you have these two, the sum rule tells you what lambda has to be. So if we do this, if we add this sum rule, this is still simulations, we converge very nicely to the exact result. So this was great. And what we then did subsequently, obviously now the idea was to test it on hardware. And that's what we did on IBM's machine. That's for 2 qubits. We were glad to see that essentially our experiment actually tracked pretty much very well our simulation, right? So what we simulated and predicted was exactly obtained then on the quantum hardware. And this is great. So this shows that it works, right? And this concludes essentially the algorithm. And what we would then pass back, just maybe to summarize, to an experimentalist, he doesn't really care about all these technical details. He just wants to see the density of states of the system, and that is shown here. So the black curve is the exact solution. The green curve is obtained with IBM's, what the curve I showed before. And at least on this scale, you cannot see the difference, right? They're basically identical. And this is great. This is really what we call a proof of concept that this algorithm works on actual quantum hardware with all the noise that we have to date. Maybe just for those that are not so familiar with DMFT, just to see why do we use it, right? I show also the non-interacting solution, which is the orange curve. So if you do not do DMFT, you get the orange curve, which is one big peak around 0, instead of this kind of three-peaked structure. Right? It's a qualitative failure here. So it's very important for specific systems to actually use DMFT. You cannot just do DFT, right? DFT will give you, say, the orange curve, right? Okay, so this kind of concludes the results that I wanted to show today. But I just want to give a bit of an outlook of where we are going with this. So clearly, we as I said at the beginning, we went from the actual physical system, did a mapping to the exact diagonalization, and then we mapped it to the smallest possible system. Now we want to go back, right, to the green arrows. First step is not easy, but I mean, is clear what has to be done. We need to add more sites, right, save more path sites to the system. Can we then describe, for example, this condo physics real system on the left? And actually the answer is no, because, well, not with any reasonable number of sites. So for example, even if I put 12 path sites, because of the peculiarities of how this condo physics works, you will not be able to describe it, right? So even if the quantum computer can do 11 or 12 path sites, which is very challenging in itself, you wouldn't get the right solution. So we need to improve the classical side of the algorithms, right? Even if you want to have a chance to do this. So this we have done, and together, especially with our colleagues in King's College, Cedric Weber's group, right, we discussed this problem with them, and actually what they proposed is essentially, instead of using exact diagonalization as I showed it before, still to use basically the same concept, but in a nutshell, the only difference now that you put the U terms also on the bath sides. So you make the bath interacting in itself. Now remember, this is just fictitious bath sides, so we can do with them whatever we want, really. There's also real physical systems that actually have a U on the bath, right? So that is known. But here it's just for us a tool to reduce the number of bath sites. And actually, with this system here with 3 bath sites that I show on the right-hand side with this MLD, we can actually very well capture the condo physics. And I show this in the bottom figure. Now, don't look at the details. The only key feature here is that to capture condo physics, the imaginary part of the self-energy has to be 0 at 0. Now, if you look at the exact diagonalization, ED, it goes to, I don't know, some random number, right? Definitely not 0. While MLD clearly goes very nicely to 0 and captures the right physical trend. And actually, we did some more analysis in this paper for people that are interested in. So basically, it shows that with this MLD, it's a very nice tool to actually capture quantum physics with a discretized bath, which is ideal for a quantum computer. So clearly, this is the way that we think, which we will essentially go in this area here. And so to conclude, maybe just the algorithm that we are following for this. As example, I take this TOV molecule on gold, right? But this can be, say, also a crystal with some, say, that requires DMFT. First step is to map the real physical system to this Anderson impurity model. Then we discretize the bath, and what we are suggesting is to use MLD rather than exact diagonalization. Again, in this example, we need 4 sites in total, means 8 qubits. So we think that's definitely doable. And then the next step is to solve the Green's function parameters on a quantum computer. And one can use VQE, as I showed today. One can use time evolution or maybe other things that we're investigating. But the key is that because this, for example, is 8 qubits, we expect that this, for example, the circuit ansatz for the ground state wave function should all be within reach that we can actually do it in practice. Last step that is important, always use some rules to clean up the noisy output if possible. So as I showed today, that's really important. And when you're there, you just loop it back and you continue, and you go back to the physical system. So that's what we're doing. What I've shown today is just a proof of concept of this for a 2-side DMFT, which has been published last year. And with this, I end my talk, and well, thanks you very much for your attention.
Thanks very much, Ivan. Very, very nice talk, very interesting stuff. I'm just looking at the Slack channel now, and I don't see any questions yet. So let me ask a question, something I was wondering. So in the classical space, DMFT is a very popular method for solving chemical systems, electronic structure calculations. And I'm wondering, just given the kind of the machinery that you've presented here, is there some mapping required to go from what you have in an Anderson impurity model with a Hubbard-like Hamiltonian to a chemical Hamiltonian? So is there some mapping of the AIM or Hubbard model parameters to a chemical system that will be necessary there? Or to put simply, how could one go from the Hubbard dimer to H2?
Yeah, it's essentially the same Hamiltonian, obviously, because once we have the Hamiltonian is a 2-side system with some parameters. For me, the way I obtain the parameters is specifically from density functional theory. But you could do a quantum chemistry calculation. And again, there's embedding methods within quantum chemistry that are slightly different from DMFT. They use the wave function, for example. We use the Green's function. But these are technical details. But in reality, it's ultimately, you always come down to a finite, one way to do it is to discretize to a finite molecule and then map it back. The specific thing here for DMFT, different from quantum chemistry, typically is that, we work on these Green's functions and these dynamical quantities, while chemists typically work on the wave function. That's really so maybe they use reduced density matrices, for example, while again, for us, the key quantity is the Green's function.
Thanks very much. I see a question here by David Munoz Ramo. What is the physical motivation for the use between bath sites?
Okay. I skipped a bit there. So there's obviously real physical systems where you have a U on all the bath sites, for example. That could come, for example, from a quantum chemistry Hamiltonian that gives you these parameters. But in this case, by putting U, what you do is you actually make the density of states of the bath richer. So while the non-interacting density of states has as many peaks kind of as you have sites, also, so the number is not so many. But if you add the U, you have a lot more peaks. So essentially, by adding more sites, you get more peaks. But by adding the U, you also get more peaks. And ultimately, that's what you need to represent the bath better, right? The more peaks you have, the more you can fit the true function of the bath. So for us, these U's are really not physically motivated, but from a fitting perspective, that this will allow us to fit the bath through hybridization function better than that. Actually, in fact, it is exponentially many. So the number of peaks in this bath density of state scales exponentially with the bath sites in MLD. So we don't need many. We will, because it scales exponentially, even maybe with 5 or 6, we should be able to really have a very rich bath.
I see. Okay. Another question here by Bruno Sengen. Can you explain why the MLDE describes well the condo physics compared to ED?
Yeah, I mean, again, people, I think this is very interesting. Actually, you can look at this paper. We're actually showing Mott Hubbard, all sorts of other models. I just showed this example here because I think it's very nice for condo. In a sense, it's still ultimately every discretized representation of a true bath will fail to describe condo physics, because a discretized bath by definition is a big molecule, right? A big molecule has always a gap. It will never have a continuous spectrum. But as in reality, right, the key is that you still need the gap to be small enough that essentially it needs to be smaller than the width of what's called the condo peak. So as long as the distance between my states in the bath is significantly smaller than the condo peak, I can resolve the peak effectively, even if it's discretized, right? So the key here is that the gap in the bath is, it depends on how many peaks you have in the bath. So if I use without this U, the MLD, so without that, I don't have many peaks in the bath. So I need a lot of bath sites to get the peaks close together until they form some sort of continuum. But because MLD gives you exponentially many peaks, you don't need many sites because you already have a lot of peaks in the bath already, and then you get almost like a continuous function. So this was done, for example, at 5 Kelvin. But obviously, if I go, I don't know, at 1 millikelvin, eventually I might be, well, it depends. If the condo temperature is 1 millikelvin, I have to say, then this will probably also break down, and we have to use more bath sites even in MLD.
I see. Very interesting anyway, Ivan. Thanks very much again. I see no more questions from the Slack channel, so I think we will leave it at that for Ivan's talk.
Okay.
And we will now take a 30-minute break and return in 30 minutes with Igor Sokolov.